All right, quickly on this one, my recording stops partway through last time on this. So, which is an even degree polynomial with a leading coefficient that's positive? F. Even, same, both ends go in the same direction and it's going up. So that's the positive part. If it was even and negative, I think there's a couple that ask about that. It would be these two. Which graph shows as x goes towards negative infinity, f of x goes towards positive infinity? So on the left side, it's going up, is essentially what this is saying. So because as x goes to negative infinity is the left side, f of x is the graph itself. So it goes up on the left, down on the right. So the left is as x goes towards negative infinity, the graph is going towards positive infinity. So, there's a few of them. C is like that. The left side's high, the right side's low. F is like that. The end behavior on the end here. And then this one is that way too. So C, D, F would be all the choices that match. Which graph is a result of a polynomial with one double root? F. F's the only one with the double. Double's a bounce on the x-axis. None of these others have that. Which graph shows the graph of a cubic function? Cubic is third degree. If it's third degree, it has two terms. And it's odd, right? These two are cubics. Even though this turns, these are a little shorter, it's not as pronounced as these. Like if you stretch this up, stretch that down, it would look similar to this but flipped. But these count as turns. So this is a cubic, 1, 2 turns. This is a cubic, 1, 2 turns. And it's odd, we know that, so it can't be anything other than either these two or that one. And that's a line, it's not a cubic. So A and D are a choice for that. Which graph is a result of an even degree polynomial with a leading coefficient that is negative? So this is, that's what that cubic tells us. But here, it's even degree, leading coefficient is negative. That's what I was talking about earlier. The ones that are even, both ends go in the same direction, and they both go down in this case, that means it's negative. Here they both go up, that's why that was positive. This is negative, and it's both of these, B and E. Which graph is most likely that of a quadratic function with a leading coefficient that's negative? Remember, quadratics are all like parabolas, right? If it's negative, that means they both point down. The only parabola we have is right here in E, the only quadratic, and that is a negative because both ends point down. So that's E. In this section, again, all of these questions will be similar on the test, but it's going to be slightly different. You just really need to know, what all, what the end behavior means, what, the degree, whether positive, negative, even, odd, positive, negative coefficient, even, odd, degree, what the terms mean, what the terms versus degree. A lot of the stuff we went over the first 2 days of this unit. All right, all is here. If a polynomial has 5 terms, it is likely a 4th degree. False. Terns plus 1 is the degree. So if it had 5 terms, it would have to be a 6th degree. If it had 4 terms, it could be 5th degree. It's always one more. Either terns plus 1 equals degree, or degree minus 1 equals terns. However you want to think about it. The graph of a polynomial function may have multiple x-intercepts. You can have as many x-intercepts as it has real zeros. This has 4, this has 3, this has 1, 1, 1, none. So, it can have as many x-intercepts as it has real zeros. So you can definitely have multiple x-intercepts, that's true. If the x is in the denominator of the expression, it's a polynomial. It is a polynomial. Remember at the beginning of this unit we talked about what is or isn't a polynomial, and things that are not are x's in the denominator, negative powers, fractional powers, or x under the radical. If it's any of those four things, it is not a polynomial. Okay. The graph of a polynomial function may have more than 3 x-intercepts. That kind of falls back to here. Sure, it can have as many x-intercepts as it has real solutions or real zeros. So you can have as many x-intercepts as it takes for the polynomial. This has 0, this has 1, 1, 4, 3, 1. So, you know, it can have a lot of x-intercepts. A polynomial must have imaginary roots. If this said may have, it would be true. Must have, you know, this has no apparent imaginary roots. It's 4th degree, I got 4 real zeros. This is 3rd degree, 3 real zeros. This one is a cubic with only 1 real, and it's got 2 imaginary somewhere. But it can have imaginary roots. It's not a must-have. For the polynomial function f of x equals 19x to the 5th minus 12x, there is no y-intercept. All polynomials have one y-intercept, and that's it. So all polys have one y-intercept. That's it. No more. Because think about what these look like. They're always continuous left to right, right? It's not like, how could it possibly cross the x more than once, right? It's not, because if it were to, it would have to like double back on itself. And then it's no longer a function. So for it to be a function, there can't be any x values that have multiple y values. So it can't have like multiple y-intercepts. It's only going to have one, and they all have a y-intercept. So that's false. And then last one, if the degree of a polynomial function is 8, it may have less than 8 real zeros, and that's true. Now, if it just said 8 zeros total, it has to have 8. But that 8 is a combination of real and or imaginary or complex. So less than 8, sure. Like this one has 1 real, 2 imaginary. So it can definitely have less real zeros. That's the key to this one, is the real part. If it didn't say real and just said less than 8 zeros, that would be false, because it has 8 zeros. All right. That's it.